multi-level inverters, what I have employed is three-level and five-level comparison, switching losses, modulation technique, and the simulation study of the diaphragm multi-level inverter by using sinusoidal pulses modulation and followed by computation and discussion. The abstract of the paper is usually the use of conventional two-level pulses modulated inverters provides less distorted current and voltage, but the cost of higher switching losses due to high switching frequencies. So multi-level inverters are emerging as a viable alternative for high power and medium voltage applications. So by using the multi-level inverters, we are going to compare the conventional two-level pulses modulated with multi-level inverters, nothing but three-level and five-level. So I will be showing that the total harmonic distortion and switching losses are considerably reduced when compared to the conventional two-level pulses modulation technique. So finally, the simulation study confirms the reduction in harmonics and the switching losses as the number of levels increases. And the objectives are to compare the topologies on the basis of switching losses and TSG at different switching frequencies, and to overcome the drawbacks in the conventional two-level pulse width modulated inverters, increasing the number of levels in the multi-level inverters so as to reduce the switching losses and harmonics. So methodology. The problem identified in my paper is cost of higher switching losses and introduction of higher order harmonics. So multi-level inverters are used to solve the above-mentioned problem, and the sinusoidal pulse width modulation technique used to control the switches of the inverter, and the diaphragm three-phase topology is considered for the study, and the MATLAB Simulink is used to design the inverters. Next. So the use of filters has a disadvantage of complete reduction. Yeah. Usually the waveforms of the practical inverters are sinusoidal and contain certain number of harmonics. For low and medium power application, square wave or quasi square wave may be acceptable, but for high voltage high power application, sinusoidal waveform with low distortion is required. So the harmonic contents present in the output of an DC to AC inverter can be eliminated either by employing filters or by using suitable PWM technique. The use of filters has the disadvantage of large size and cost. So PWM technique reduces the filter requirement to zero or even to minimum depending upon the type of the application. There are some noticeable drawbacks in the conventional two-level pulse width modulated inverters, such as production of common mode voltages, more switching losses, introduction of higher order harmonics, large change in voltage by change in time, and production of voltage sharing in series connected devices, and requirement of switches with very low turn on and turn off time. So multi-level inverters are emerging as a viable alternative for the high power and medium voltage application. So these are found to be better counterparts for the conventional two-level pulse width modulated inverters, and the features are the less switching stress on the device, and high voltage and high power capability, and reduce harmonic contents without increasing the switching frequency, and reduce switching losses, and reduce the harmonics, and good electromagnetic capability, and followed by many advantages. The basics of the two-level inverter. It's the most widely used topology for the various low and medium power applications. The full-pitch configuration of voltage of the inverter is shown in this figure, and the switching states for a 120-degree mode of operation is given in such a way. And disadvantages in two-level. So they suffer from the static. Usually the power devices are connected in series in parallel connection, right? So, but they suffer from the static and dynamic voltage sharing problems in series and parallel connection of power devices. Here the power devices have taken a MOSFET. So the high rate of change of transfer due to series commutation of the devices. Usually the multi-level inverters can be designed in three ways. It's diode clamp, capacitor clamp, and cascaded multi-level clamp. In capacitor clamp, both the real and reactive power can be controlled, but it suffers from the real power transfer, so it requires high number of storage capacitors in the higher levels. So in this multi-level inverters, we are going for the higher number of levels. As we go for the high number of levels, we require large number of storage capacitors. So we are regulating this capacitor clamp. In cascaded clamp, also they require large number of DC sources for each of the bridges. So what I am doing is, why diode clamp three-phase topology is considered. In this topology, all the devices are switched at fundamental frequency, resulting in low switching losses and high efficiency. So the control reactive power flow between source and load, it's a simple topological structure. The control logic is simple, especially the back-to-back interconnection of the two systems. Next. So however, it requires a large number of clamping diodes for a large number of output voltage levels. To design the 3-level and 5-level, we should use this one. We require for M-level inverter, we require M-1 switches for each half wavelet, and M-1 DC link capacitor, and M-1 into M-2 clamping diodes for each half wavelet. So first I am going to design the 3-level diode clamp multi-level inverter. For this we have 6 clamping diodes, 12 power switches, and 2 DC link capacitors. Next. So middle point of the DC bus capacitor is nothing but the point N. The main piece of topology is all the clamping diodes that clamp the switch voltage to half the DC bus voltage reducing the voltage stress of the device. So the output voltages are positive, 0 and negative, and the voltages are plus VDC by 2, 0 and minus VDC by 2. Next. So these are the switching states for the phase A of the 3-level inverter. For the 5-level inverter, as the number of levels increase according to the M-1 DC capacitor and according to that strategy we design. So we have 36 clamping diodes, 24 power switches, and 40. So the circuit is a little bit complicated, but as the number of levels increase, I want to show that the THD and switching losses are reduced when compared to conventional. We have 4 DC capacitors. Next. So the voltage across each capacitor is VDC by 4. So the switching stress across the device is also limited to VDC by 4. So the table shows the ones and zeros, which represents the 1 is which is in on condition and 0 represents which is in off condition. Next. Okay, switching loss calculation. So consider a MOSFET switch connected across a DC voltage of value VDC. So the VM and IM are nothing but the voltage across and current through the MOSFET. Let's go. So this is nothing but the ideal switching characteristics of a MOSFET. Next. So V of T and I of T are nothing but the voltage and current during the TC on, turn on crossover interval. And instantaneous power is nothing but V of T is nothing but V of T into I of T. Next. So EC1 is nothing but the integral of the power, what we got. So the same thing we will do for the turn off crossover interval. So VT, IT. Next. So the power for the turn off crossover interval is V of T into I of T. So we get the equations. So finally we get the equations for the average switching losses. So finally we get the average switching losses TSW in the switch. Why we have calculated this equation is in order to develop the simulink circuit in the inverter. So the equation 11 of the final equation of the switching losses shows the switching loss in the semiconductor switch varies linearly with the switching frequency and switching length. So modulation technique. We can go for different multi-level voltage source inverter techniques. There are pulse width modulation and step width. In step width we can go for harmonic elimination, and in pulse width modulation we can consider either open loop or closed loop. In open loop, sinusoidal pulse width modulation, space vector, sigma delta. In closed loop we have all current controllers, step bit controllers and so on. So what are techniques in the open loop? Sinusoidal pulse width modulation technique. So in sinusoidal modulation techniques, a triangular carrier wave at high switching frequency is compared with sinusoidal modulated signal with fundamental output frequency. So if we want to employ M level inverter output voltage, we require M-1 carriers. So I'm going for 3 level and 5 level. For 3 level, we require 2 carriers, M-1. So for 5 level, we require 5-1, 4 carriers. Next. So this is the pulse generation of the 2 level inverter. I've taken one triangular carrier pair and one sinusoidal reference pair. So I'll get the pulse generator. Next. This is for the 3 level, 2 triangular carrier pairs with one sinusoidal reference pair. So for the 5 level, I have 4 triangular carrier pairs with only one sinusoidal reference pair as comparison. So this is the simulation diagram. This is the basic inverter. This is the mouse here. So this is the basic 3-phase, 2-level, multi-level inverter. It's given to the 3-phase voltage current measurement, which is phase to phase, and it's given to the RL load. So for RL load, I have taken the active power as 8 kilowatt and reactive power as 6 kVAr. So from this, I have calculated the resistance value is 3 ohms and the inductance value is 12.7 millihenry. And this is the scope where we can see the inverter output voltage. It should be on sinusoid. And these are the voltage which is given to this part, and this is nothing but the THD of the frequency 50 Hz, and it's given to the scope. This is nothing but the switching loss calculations what we have calculated from the ideal switching characteristics of the MOSFET. So this is for the 3 level, and this is for the 5 level. So this is the inner subsystem of the inverter. What we use is 6 MOSFETs. This go to and from blocks which are used in order to simplify the, in order to reduce the complexity of the circuit, we are going to go to and from blocks. And this is the model, MATLAB model for the 3-level double clamp inverter, where the switches are increased and even the diodes and DC link capacitors. This is for the MATLAB 3-phase for the 5-level inverter. This is the subsystem blocks. This is nothing but the control circuit, which is nothing but we are comparing one sinusoidal reference wave with one triangular. So we are comparing with the relation operators greater than equal to 1, it directly go to the S1 to the inverter. If it's not, it will go to the S4. The same thing, one modulating signal is compared with the 2 triangular. And for the phi level, one sinusoidal modulated signal is compared with 4 triangular carrier. So this is the output voltage waveform for the 2-level inverter. It's a sine wave, but it contains lots of harmonics. So when compared, if we go for 3-level, the frequency spectrum, if we go for 3-level, the performance is still more improved. It's close near to sine wave, but it's not completely a sine wave. But go for 5-level, we got the exact sine wave, which is applied for the high voltage, high power application. So these are the switching losses for a 2-level inverter, different switching frequencies ranging from 1500 Hz to 5000 Hz. So these are nothing but PHC. The PHC is reduced upon increasing the switching frequency. The switching frequency is a manual one. We should give in the command window of the MATLAB. I'll give the 1500, so that I get the respective values. For the 2500, I get the respective values of the total harmonic distance. And I'm going to also another aim of my project is the optimized switching frequency with respect to the PHC and switching losses. See, we can see at 2300 Hz, the losses are getting optimized. This is for the 3-level inverter, and these values what I got is according to the values, the parameters what I have taken for the MOSFET parameters. See, this is for the 5-level. The optimized switching frequency what we got is about 2300 Hz, and this is for the 5-level. I'm going to compare the 2-level, 3-level and 5-level, the switching losses. The switching losses are considerably reduced. The green one indicates for the 5-level, and the red one indicates for the 3-level, and the blue one indicates for the 2-level. This is the percentage of THD for the 2-level, 3-level and 5-level. We're comparing all the levels. So for the 5-level, it's considerably reduced. So the conclusion. So it has been observed that the THD and switching losses decrease with increase in the number of levels. And from the figures, we can say that optimize the switching losses and harmonic contents for the operation of the inverter at optimized switching frequency. And the above investigations are made without the application of the filter. So by using the filter requirement, the harmonic content can be still more be improved in the future scope of work. So even I have done the same thing by the use of induction motor. I have replaced the RL load and I use the induction motor load. And there is a slight change in the values of the THD and switching losses. And these are my differences.
Thank you, Mr. Phani Chandra. The switching losses you have given how to calculate, but what is the unit in which you are giving the switching losses?
I have just taken a MOSFET, sir. According to the parameters, I have calculated the losses.
You have given MJ. Switching losses MJ. What do you mean by MJ? Millijoules. Millijoules is a very small. The losses is only that much, you are sure?
Yes, sir.
Okay. Then you said that you are finding the optimum switching frequency because the two curves are optimum the optimum point. Does that optimum point vary with the level of the inverter, 3-level, 5-level, it will vary? How they are operating point? Is it constant or that also varies?
Actually, till now, for the whatever work I have done for 2-level, 3-level, 5-level, it is constant.
It is
In
constant.
the future scope of work, I'm not sure. I'm not giving the word that it may vary. I'm thinking it may vary. The offshore switching frequency. I'm just going to find a of course, the levels are
change the number of
See, you mentioned that you tested this circuit with an induction motor. What is the rating of that induction motor?
no, sir. Defaultly, I have taken some values. Whatever values they're there in the parameters itself from the simulating block data.
taking the default induction motor model is
I just applied.
What
main work what I have
what is that voltage? What is that rating? Wattage? How much?
No, I have just checked, sir. Not
Is it a 1 kVA induction motor or is it a 2 kVA induction motor?
So from the simulating block set I have taken.
1 horsepower or 2 horsepower, what it is?
to the library. No? You
Yeah,
should have noted down and
I-
answer.
Because the problem is, when you say multi-level